Hello. Hello, everyone. I am in a new location. I finally moved. It probably doesn't look very different from my previous location, but it is another. It's in a different place. So yes, good to see you all. And I hope you can hear me. If not, let me know. And we'll start. So today I've got some physics questions for you, and I've got some maths questions for you. So we'll start with a very interesting but a very difficult physics problem. So this is one of the extra problems in the assignment. Oh no, it's not. It's actually the last question in the assignment. It is the last question. It's not problem 20, but it is in the assignment. So I'll go through like 95% of it, and hopefully you can figure out the rest. And let me share my screen. Okay. Please let me know if you can see my screen. Okay, perfect. Right. So the idea, this is the section in the assignment where you need to use energy to sort out kinematic properties, kinematic values. So for example, find the acceleration using energy. So why would you use energy? Well, if you look at this question very carefully, you'll see that it's not really solvable by traditional kinematics. A heavy rope of length L is folded in half and held at both ends at a single point above the ground. One end is released and starts moving down. Find the acceleration of the free end of the rope when it has fallen a vertical distance L over 3. Assume that there is no swing and no energy dissipation. So on one hand, it seems like this end of the rope is in free fall. Is in free fall. The acceleration should be g. Because free fall. But the problem is that the mass of the falling part of the rope constantly changes. So if we say GPE turns to kinetic energy, now it's the whole mass of the rope falling, but only a tiny piece. Like, let's imagine you are at the end of the process and you are left with only this part of the rope. So this is the moving part of the rope. This is moving, and the rest is stationary. So all of the gravitational potential energy of the rope, which has fallen, has to go into that small piece of the rope, which has a very small mass, and therefore has to have a very high speed. So you can't use the free fall because the mass is constantly changing. Mass changing. So yeah, moving, and this is stationary. So acceleration is not g. So I can assure you that the acceleration is not g. Oh. Also, I'd like you to tell me, where in real life do we see a situation like this? Any suggestions? A rocket. Whips, yes, whips. Yo-yo. Well, yes and no. In a yo-yo, the string is very light. We're talking about a heavy rope. And the yo-yo, well, no, it's not a heavy rope. Yo-yo is much heavier than the rope. Bungee jumping. In a bungee jump, a person is attached to a heavy rope, which is falling. So yeah, this is a bungee jumping question. All right. So let's work through this problem. It's a big one. It's not easy. So at any point, if you lose me, please ask questions, because I don't want you to get lost. Do tell me if you don't understand something. So we have the rope. We're going to model it like this. So initially, we have two pieces of rope. We can ignore the bottom bit. Two pieces of rope, length L/2, L/2. The center of mass is here. Let's introduce an axis, and it's going to be downwards, the x-axis, and this is 0. 0 is on the x-axis. So this point is L/4, of course, because the length of the rope is L/2, and this is going to be L/4. Okay. Right. Let's say this rope has moved down slightly. So the rope has moved down slightly. So this end of the rope is longer, and this end of the rope is shorter. So the rope has moved down a distance of x. The distance of x. Right. So we need to find the length of this piece of rope, and we need to find the length of this piece of rope. Well, there's x extra, which is split between the two pieces of rope. So the extra x is hanging here. So this is going to be x/2. So the length of this piece of rope is L/2 plus x/2. And the length of this piece of rope is L/2 minus x/2. And you can see that if you add these together, you get L. So that makes sense. Okay. Everything good so far? Let me know if I lost you. Okay. Now, the center of mass of this piece of rope is here, and the center of mass of this piece of rope is slightly lower. So we need to find this distance. We need to find x1 and x2. x1 is the center of mass of the first rope, and x2 is the center of mass of the second rope. So x1 is going to be half this, so L/2 plus x/2 over 2 plus L/4, because that's the, oh sorry, minus L/4, of course, because that's this length. This length is L/4. And we only need, because this is the 0, we're counting from this line, not from the top. Okay. So from the top is going to be L/2 plus x/2 over 2, but from this line is going to be L/2 plus x/2 over 2 minus L/4. And we can simplify this as L/4 plus x/4 minus L/4. L/4 cancels, and it's going to be x/4. So the center of mass of the first piece of rope has moved down by x/4, where x is how much this end has moved. x2 is going to be the midpoint of this one. So it's L over 2 minus X over 2 over 2 plus X minus L over 4. So because it's moved, we're counting from here plus X and then subtracting L over 4. So it's going to be L over 4 minus X over 4 plus X minus L over 4 is going to be 3X over 4. How much sense does it make so far on a scale of 0 to 10? Please give me a number. Okay. So we are just looking how much the center of mass of the first rope and the second rope has moved down. And the first piece of rope has moved down by X over 4. And the second has moved down by 3X over 4. If you get lost in the maths, that's still fine. You can still appreciate. So if this end has moved down by X, this has moved down by X over 4, and this has moved down by 3X over 4. Okay. Now we need to find how much the center of mass has moved. So we need M1, the mass of the first rope, and the mass of the second rope. The mass of the first rope is going to be the length of the rope is a fraction of the length. So it's L over 2 plus X over 2 divided by the length of the whole rope, L, and multiplied by the mass of the rope. So it's going to be it's going to be L plus X over 2L times M, where M is the mass of the rope. The mass of the second rope is also a fraction of the rope. So it's L over 2 minus X over 2. That's the length of that piece divided by L multiplied by M, which is L minus X over 2L M. And finally, we can find the center of mass of the rope. You can find the center of mass of the rope. Center of mass, which is, as you already know, is M1x1 plus M2x2 divided by 2L. Okay. What? Sorry. What am I saying? Divided by the total M1 plus M2. And M1 plus M2 is simply M, right? It's the total mass of the rope. Okay, I'll write it down. M1 plus M2. So that's M. So M1, we just substitute very carefully. So M1 is L plus X over 2L M multiplied by X1, which is X over 4, plus M2, L minus X over 2L minus multiplied by X2, so 3X over 4. All right, and times M. So M cancels, which is good for us. So there's going to be 8L. We can drop that down, 8L, and this is going to be L plus X times X plus L minus X times 3X. Can we simplify that? And so it's going to be Lx plus x squared plus 3Lx minus 3x squared over 8L is going to be 4Lx. So it's going to be x over 2 minus x squared over 4L. This is the center. This is how much the center of mass has moved. So the center of mass of the rope was here, and now it is somewhere here, and the distance that it has moved is this. Right? Any questions? Don't be afraid to ask. This is just a bit of reasonably complicated arithmetic, well, algebra technically. So there's nothing extraordinary here. The extraordinary bit comes in right about now. This is the amount that the center of mass has moved down. Therefore, the change in gravitational potential energy is the mass of the rope, G, times delta H, which is this, delta H, is the change of the position of the center of mass, which is mg x over 2 minus x squared 4L. But all of the kinetic energy is transferred only to the moving part. Kinetic energy, this gravitational potential energy is transferred to the kinetic energy of the moving bit of the rope. So this energy is transferred to the moving bit of the rope. So the change in kinetic energy is 1/2 m2, because that's the second part of the rope, multiplied by velocity squared. Velocity of that bit. All right, so it's 1/2 multiplied by m2, which is L minus x over 2L, multiplied by m, multiplied by v squared. And because of conservation of energy, these two have to be equal. Right, so mg x over 2 minus x squared over 4L equals 1/2 L minus x over 2L times m times v squared. So m cancels. As usual, when something is falling, m cancels. The mass of the rope cancels. And we just open the brackets. So there's nothing serious here. So gx over 2 minus gx squared over 4L equals L minus x over 4L multiplied by v squared. And we can multiply the whole thing by 4L, and that's going to be 2LGX minus GX squared equals LV squared minus XV squared. What are we looking for? Somebody remind me. What are we looking for? Yes, thank you. Thank you for the reminder. We're looking for the acceleration. But this equation does not contain acceleration. Or does it? How can we find acceleration from this equation? Differentiate. Well done. Thank you. We need to differentiate this expression to get acceleration. And we need to do this very carefully. So we differentiate with respect to time. Differentiate with respect to time. So L and G are constants. So the derivative of the first bit is just 2LG dx dt, which is V. Okay, you know what? I'll just write dx dt. X dot, you mean? X dot is V. Minus. Now this is a chain rule. So it's G is a constant. So it's 2x multiplied by dx dt. Yeah, because dx squared dt can be written as dx squared dx multiplied by dx dt, which is 2x dx dt. So it's a chain rule. I hope you all know this. So yes, equals L. Now this is a chain rule again. So it's going to be 2V multiplied by dV dt. And here we need to use the product rule and the chain rule. So it's minus x dash v squared minus x v squared dash. So this is minus dx dt multiplied by v squared minus x multiplied by 2v multiplied by dv dt. Okay, and now we can write this 2LG, well, dx dt is v minus g 2x dx dt minus to gxv equals 2LV multiplied by acceleration minus this is dx dt, so that's v multiplied by v squared minus 2xv times acceleration. Now v cancels, makes life a bit easier, and we just need to make a the subject. So we take v to the other side, so it's 2g L minus x plus v squared equals 2a 2a L minus x. So divide both sides by L minus x, and we get acceleration is equal to g plus v squared over L minus x. Can somebody notice something extraordinary about this acceleration? After all, it is a free-falling rope. Yes. Thank you. It is faster than G. Yes. Free falling rope, but acceleration is greater than G. And it is true for a bungee jumper. If you look at any bungee jumper, if you look at a video of a bungee jumping and you make measurements, you will see that they are accelerating faster than G, which I find absolutely fascinating. Like, and it's understandable because you're being pulled down by the rope, and then the energy of the rope goes into your kinetic energy because the rope stops moving after it's unfolded, but the person continues to accelerate. But still, it's quite cool. And all you need here is to find. This is not the answer, because you need a very specific answer. It says you find the acceleration of the three end of the rope points has fallen in a vertical distance L over 3. So that's x. X is L over 3, but also you'll need to find the velocity. So you'll need to use one of these equations to find the velocity. So for example, this one, find the velocity. Yeah. Well, actually, we could work out v squared from here. You can get v squared. You can get v squared, and then you can substitute that into here. This will also work. Depending on if I is greater than x. Well, L cannot be greater than x because the rope cannot fall more than its length because of the way it's designed. It can fall a maximum of L. And also, when at the end, as x approaches, also what you should notice, as x approaches, well, as x tends to L, this is a what's it called? It's a singularity. So A but tends to infinity. So at the end of your route, your acceleration approaches infinity. Well, which is obviously not true because of the way ropes are not perfect, and the energy will be absorbed. After all, the energy will go into the vibration of the rope. It will go into air resistance and all sorts of things. So don't worry. If you do a bungee jump, you won't be torn into pieces by the infinite acceleration at the end. Probably. But theoretically, with a perfect rope of infinitely small, it has to be an infinitely small rope, etc., etc., etc. So the model breaks down. The model breaks down when x approaches L. So we don't know what's happening at the end. and it will swing sideways. The end will swing sideways as well, causing the whole rope going into vibration. So this will not happen, but the model predicts this. So it's an imperfect model. Right. So I don't know about you, but I find this problem really, really fascinating, because there's so many things that are counterintuitive, such as the acceleration is greater than g in free fall. Yeah, I'll just move this here. So, and just not the answer. So this is not the answer. Okay, the next one. The next problem is 18. It's easier, although it's one of the harder problems. So it starts gently. So we have a point-like object with mass 1 kilogram starts from rest at point x equals 10 meters. So it starts here and moves without friction under force F. And this is the graph of the force. The motion is confined to one dimension along x. What is the speed at x equals 0? So what happens? So the body starts at x equals 10 meters. And as you can see, the force is backwards. So basically, this is 0. This is 10 meters, and you start with the force, which is backwards, F, which is minus 10. And as it moves this distance, as it moves to 0, work is done. So force times distance moved is 10. So the work is force times distance, which is 10 times 10, which is 100 joules. So the force does 100 joules of work. It's not negative because the force is minus 10, but the displacement is also minus 10. So minus and minus make plus. So minus 10 times minus 10 is 100 joules. So basically the force accelerates the object to 10. So at point 0, it has kinetic energy, and because of work energy principle, so the change in kinetic energy is equal to the work done. So the kinetic energy is equal to 100 joules. 1/2 mv squared is 100. So 200, so m is 1, so v squared is 200. 200, so v is 14.1 meters per second. Is 14.1 meters per second. Sketch its kinetic energy as a function of x. Well, the kinetic energy increases by the same amount with each step. So the kinetic energy and x. So starting from 10, it's going to increase to 100. Okay. Starting with 10, it's going to increase to 100 like this. Meters. It's 100 joules. Because it increases uniformly, because this is a constant force. So the kinetic energy is equal to force times distance. So force is 10, and the displacement is s. So it's a linear relationship. Sure. Okay. Right. So once we are past the 0, force starts changing differently. So we can write down the expression for force. Force is -10 minus x. Okay, this is the little straight line. The straight line for force, and I worked out the equation. -10 is the y-intercept, and -1 is the gradient, so it's -10 minus x. And the displacement is minus x technically. The displacement, so past 0, f is equal to -10 minus x, and the displacement is minus x because we're moving backwards, right? We're moving. So the change in kinetic energy is equal to force times distance. So it's force times s. So it's going to be -10 minus x multiplied by minus x. So it's 10x minus x squared plus 100, because at 0 it has 100. No, sorry, that's the change in kinetic energy. So the kinetic energy is equal to 100 plus the change in kinetic energy. So it's 100 plus 10x minus x squared. And you should know parabolas by now. The parabolas is so it's going to be a parabola with a maximum at -10. And it's going to be like this. Interestingly, would be good to find where it crosses the axis, and it's square root of 75. Square root of 75, is it? No, I don't think so. Sorry, so that's mode equation. So -1, 10, 100. Minus it's 16, -16. So what happens at this point? Well, at this point, it can't be. It's on -16. Sorry. Must be something like 26. I don't know what went wrong. I'll leave you to work out where it crosses. But anyways, the kinetic energy is a function of x, and it's a quadratic, and it's a parabola, upside down parabola. And the maximum of this parabola is going to be 150 joules. So why is that? Well, look, you have the first, this is the amount of work done. That's 100 joules. And then there's another 50 joules done of work. So the maximum kinetic energy is 115. And then you start decreasing. That's 50. That's another 50. And that's 100. So yeah, it looks like it's going to be 26. So somewhere 26. I don't know what went wrong. Why I go to 16. Minus 1, 10, 100. Of course. Still doesn't explain it. There's going to be plus. Let's see. 1, 2, okay. Something went wrong. I can't see it. Sorry. At the end of the day, I'll figure it out. Acceleration. So the velocity. Well, the velocity you get from the kinetic energy. Yes, because if you know the kinetic energy, you can sketch the velocity as well. So the velocity is just the square root of the kinetic energy. So basically, if we get a correct expression for the kinetic energy, which we don't, unfortunately, so the velocity is the square root of 2 times the kinetic energy divided by the mass. The mass is 1, so square root of twice the kinetic energy. And I'm just going to tell you that the graph will look like this. It's going to be very similar to kinetic energy, just slightly different. So minus 10, 10. This is 14.1. Oh. There's going to be 2 curves. They're not, it's not a single curve, it's 2 pieces, pieces of curve. I think I have a better picture somewhere here. Yeah, so this is how it's going to look like. So you can see that the it stops at minus 20, minus 26 point something, 20, 27 point something. And there's a 14.1. That's the top speed. Then speed here is 0. That's the initial speed. Okay. Right. I'll skip the rest of the question, just to get moving. You can find the solutions. You can find the solutions, and I'll send you the link. So here's the, you can find the solution here. Okay. Now problem 16. How much time do we have? Do we have 3 problems? Yeah, just about enough time. So problem 16, it's a general problem. It's not particularly difficult to work it out. A 2-meter tall bird watcher with a mass 100 kilograms sees a nest in a tree. When he stands 18 meters away from the tree, the line of sight makes an angle 45 to a line parallel to the ground. Okay. Sees a nest in a tree. So a bird watcher sees an egg fall from. How long does it take to reach the ground? So we have a tree. Okay, apologies. Yeah, we just and a nest. There's a nest in a tree, and the bird watcher is standing 18 meters away. 18 meters away, and the line of sight makes, so he's 2 meters tall, and the line of sight makes 45 degrees to the horizontal. 45 degrees. So you can work out, using trigonometry, you can work out the height of the tree, the height of the nest, h, and the height is 2 meters plus, so 18 here. That means this is also 18 plus 18, so that's 20 meters. So the nest is 20 meters above the ground. Okay. So this is simple trigonometry. Then we can say how long does it take to reach the ground? Well, it's a subat. Yeah, so it's S is equal to 1/2 AT squared or GT squared. So T is equal to 2S divided by G square rooted. So that's 40 divided by 10. So that is 2 seconds. So the answer is 2 seconds. How fast the egg is traveling when it reaches the ground? So here you can use conservation of energy, 1/2 mv squared. So that's question A. Question B, mv squared is equal to mgh. So v is equal to square root of 2gh. And that is 20 times 20. That's 400, square root of 400, which is 20 meters per second. It's a useful thing to remember. If you fall from 20 meters, you will hit the ground at 20 meters per second. Also, if you're falling for 2 seconds, every second you accelerate by 10. So that's obvious. I should have used conservation of energy. Every second you increase the speed by 10. So in 2 seconds, it's going to be 20. That's very obvious. Right. C, the egg strikes the ground and is brought to a stop in a distance of 1 millimeter. Assuming a mass of 20 grams for the egg, calculate the force required. Right. So we have an egg traveling at 20 meters per second and has to stop within 1 millimeter. So force times the distance to stop has to equal to the kinetic energy. So that's the work energy principle. Alternatively, you could use momentum and momentum calculation. So change in momentum is equal to force times delta t. Although it does move, it says it has to stop in 1 millimeter. So that's not easy because you still need to work out the time, and for time you will need to use subat. So I would use the work energy principle. So force times distance is the kinetic energy. So the force multiplied by 1 millimeter, 0.001 meters, is equal to the kinetic energy, which is mgh, which is 1/2 mv squared. mv squared, which is 1/2 multiplied by 0.02. That's the mass of the egg, 20 grams times 400. So that is, the force is 0.01. 0.01 times 400 divided by 0.001. 4,000. That's 4,000 newtons. That's a big force. 4,000 newtons. Calculate the work done by this braking force compared with the gravitational potential energy of the egg. Well, that's obvious. The 4,000. So the work is 4,000 times 0.001. 4,000 times 0.001. That's 4 joules. And the mgh is equal to 0.02 times 10 times h, which is 20. 0.02 times 10 times 20. That's 4 joules. This has to be the same. There's no other option, because gravitational potential energy turns into kinetic, and kinetic is reduced by doing work on the egg. by doing work stopping the egg. E, right, I'll carry on here. E, unsurprisingly, the egg is smashed by the impact. To prevent this happening again, the birdwatcher places a pad of foam which is 10 centimeters thick around the tree. This responds to impacts by compressing to half its initial thickness. Find a new braking force. So now the distance that it moves, the force times the distance, is still mgh, or yes, mgh. I'll find a new braking force when the second hole and the time taken for the egg to go to a halt. So force multiplied by now it's 5 centimeters, 0.5 equals, we know that this is 4 joules. So F is equal to 4 divided by 0.05, which is 80 newtons, which is much lower, as you can see. And the time is, well, we can find the acceleration. Acceleration is the force divided by m. So it's 80 divided by mass, 0.02. 0.02. It's 4,000 meters per second squared. And the time is the change in velocity divided by acceleration, which is 20 divided by 4,000. So 20 divided by 4,000 is 0.005 seconds. That's the time it takes to stop. The birdwatcher considers the possibility of returning the egg to the nest by climbing the tree. Calculate the minimum energy he would have to expend to achieve this. So F. Well, that's mgh. That's easy. Mgh, that's equal to 100 kilograms, I believe. Yes, 100 kilograms times 10 times 20. Although, I mean, he doesn't need to climb to the top of the tree, so his center of mass only needs to move 18 meters because he can then reach. So I would say 18. So he only needs to climb 18 meters. Although there's no, if you say 20, it's going to still be correct, as long as you explain. So that's going to be 1,000 times 18. 18,000 joules. That's the energy required to climb the tree. And of course, being a very kind fellow, he decides to use this energy to boil the egg instead of using a small electrical heater powered from a hand generator. Calculate the minimum energy efficiency required for the system so that it requires no more effort to boil the egg than to return it to the nest. Assume that the egg has a specific heat capacity of 4 kilojoules per kilogram, the same boiling point of water, and starts at 20 degrees. So to boil, we need to, so the energy required is mc times the change in temperature. So the mass is 0.02 multiplied by C, which is 4,000. That's the specific heat capacity of the egg, and then times time. So it starts at 20, needs to boil, so it's 100 degrees. Sorry, 80 times 80. So that's 0.02. Times 4,000 times 18. So 6,400 joules, and the efficiency That's the useful energy. Useful, and this is total. So the efficiency is 6,400 divided by 18,000, which is 18,000. 36%. 36. If you calculated 20 as the height. So boiling eggs aside, I really like this question because of so many calculations and so much. I think it brings all these things like kinetic energy, gravitational energy, thermal energy into one place. Yes, forces, impact forces, so momentum pretty much. So you kind of get an overview of the whole thing. It's a very nice question. I advise you to do it over again by yourself because it's just yeah, it's elegant. Yeah, except the boiling of the eggs, of course. Right. Problem 15. Now, of course, I prepared 2 maths problems for you, and I'll just show you my approach to them. This is not a single correct approach. So this is one of the math problems. I think it's one of the extra problems, so one of the optional. ABC is a parallelogram. AB is square root of 3/2, 3 square root of 2. AD is 8, BAD, M is a point on CD. So first, we always start with a diagram. Usually ignore. A, B, C, D. Okay. Now I'd like to introduce a coordinate system. So this is going to be X, and this is going to be Y. So what do we know? We know AD is 8, so this is 8. So D is 8, 0. A is 0, 0. B. Now this is 3 square root of 2. So what are the coordinates of B? Somebody tell me. You can shout out. And how do you know why? Three. Well done. Yes. Thank you, Andre. Three. Because this is 3 square root of 2. This is 45 degrees. So this is, using trigonometry, this is 3 square root of 2 times cos 45, and it's 3. So I'm just going to write this separately. 3 square root of 2 cos 45 is 3, and 3 square root of 2 sine 45 is also 3. So that's 3. So hence this is going to be 3, and 8 plus 3, 11. Now point N is on AD, and it's 3 to 1. 3 to 1. So it's going to be 4.5. So N, because we know that the AN to ND is 3 to 1. And in total there are 6, so 3, so it's N has coordinates 4.50. And M has a ratio 1 to 2 to 1. CM to MD is 1 to 2. So it's 1 to 2. And you can see even from the diagram, see the reason why you do a diagram, you can work it out. You can immediately see that if this is 1 to 2 and this is 3 squares, and by 3 by 3 squares, M has coordinates 10, 2. So a diagram is a very powerful tool in your maths. You can prove it. You can prove it if you need it, if you need to, but a lot of things become clear from a well-drawn diagram. So we need to find the length of AM. Oh, that's easy. You just use the formula for. Well, I'm gonna draw the vector AM is 10, 2. So the length of AM is the length of the vector AM, which is square root of 10 squared plus 2 squared, which is square root of 104. Now BN is also a vector, and BN, so that's 1.5 minus 3, because it's N minus B, and BN, the modulus of BN is 1.5 squared plus 3 squared. It's going to be 9 plus 1, so it's going to be 10.25. No, sorry, I got N wrong. N is not 4.5. N is it's 8, so it's 6. It's 3 to 1. Yes, sorry, it's 6. Oh, nobody stopped me. So that's not that's going to be 3. And that's going to be 3 squared. So that's going to be 3 square root of 2. 3 square root of 2. Now the interesting bit, the angle between BM and BN. So that's A, B, C. So we know the cosine of the angle between AM, cosine theta. So this is AM, and this is BN, and we need this angle. Cosine theta is going to be AM multiplied by BN. That's the scalar dot product divided by modulus AM modulus BN. Okay, so AM times BN, so 10 times 3, So it's 30 minus 6 over AM is square root of 104. And this is 3 square root of 2. So it's 24 over square root of 104 times 3 square root of 2. And theta is our cos of that, cos minus 1 of that. So it's 8 over square root of 208. So that should be 56.3 degrees. Okay, any questions? Any questions here? Like this is using coordinate method, so I'm using vectors. Vectors is part of the coordinate method. You don't have to do it like this, but it's very useful. When you're not given the coordinates, but you can introduce them and solve pretty much any problem. It's sometimes easier using the coordinate method, sometimes it's not. So this is another arrow to your wherever people keep arrows. Another question, which is not particularly difficult. ABC is an equilateral triangle with side 12. M is a point on BC, such that the ratio of the areas is 1 to 5. Find the length of AM. Find the angle AMB. All right, so we start with drawing a diagram, as usual. Introducing a coordinate system. This is what you do in physics a lot, introduce coordinate systems. So you have X, Y, this is 0, 0, this is A, this is C, which is 12, 0, and this is B, which is, so it's 6, and 6 square root of 3, because this is 60 degrees, this is 12, so 12 cos 60 is 6, and 12 sine 60 is 6 square root of 3. All right, then point M is on BC, such that the ratio of the ABM is 1 to 5. So M is here. Okay, so how do we find? Well, if the ratio is 1 to 5, if the ratio is 1 to 5, that means if you take a triangle, and you have a point like A, okay, B, M, C, A. So area of triangle ABM, because the height of the triangle is H, is equal to 1/2 the base BM times the height, and area of AMC is 1/2 times the base, which is MC, multiplied by H. So the ratio of the area A1, let's call it A1 and A2, A1 to A2 is 1/2 BM times H, 1/2 MC times H. 1/2 cancels, H cancels. So the ratio of the areas is the ratio of the lengths, MC. Okay, so the ratio of the areas is, so the length, the ratio of the length is 1 to 5 as well. So BM to MC is also 1 to 5. Right. So we need to find the vector BC. BC first. And BC is C minus B. So it's 12 minus 6, so that's 6. And 0 minus 6, so it's minus 6 square root of 3. Now BM, vector BM, is a sixth of the vector BC. So it's going to be 1/6 times 6 minus 6 square root of 3, which is going to be 1 minus square root 3. This is the vector BM. Finally, find where what do we need to find? Sorry, length of AM. So AM, vector AM, is AB plus BM, and that's AB, which is 6 square root of 3, plus BM, which is 1 minus square root of 3, which is 7 and 5 square root 3. So the length of AM using Pythagoras, square root of 7 plus squared plus 25 times 3. So 49 plus 75. 49 plus 75 is square root of 124. Yeah, that's the answer. So that's A and B. The angle AMB. 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 Well, we need the angle. So cos of angle AMB is AMB is MB multiplied by MA divided by modulus MB times modulus MA. Right, because we're looking for this angle, theta. So it's MB and MA. It's the angle between these two vectors. So MB is minus 1 square root of 3. So it's BM is 1 minus square root of 3, and MB is the opposite. Multiplied by MA, which is minus 7 minus 5 square root of 3, divided by MB times MA, MB modulus MB is equal to square root 1 plus 3. It's 2. Oh, well, yeah, it does make sense that it is 2. 2 multiplied by modulus MA, square root of 124. So that's 7 minus 15. Yeah, 3 times 3 is 7 minus 15 divided by 2 times square root of 124. So it's minus 4 divided by square root of 124. And we can work out the angle. Angle AMB is our cos of -4/124, and it should be an 2's angle. 2's angle. Oh yeah, it's 111 degrees. It's approximately 111 degrees. Okay, good. So this is the approach. So the logic here is you have a problem and coordinates are not even mentioned in this problem. And yet you can use coordinates effectively. And that's what the assignment is all about. Okay. Can I ask, how difficult did you find the physics assignment on a scale of 1 to 10? So 10 being very difficult. How difficult is the physics assignment for you? So just to get a feelings difficulty. So that's physics 07. How difficult did you find the physics? 6. 7. So 7-ish. There are 9 people here. Come on. The question was, how difficult did you find the physics assignment? Okay. What was the most difficult part? Or what was difficult about the physics assignment? Anything particularly difficult? Anything particularly difficult? Question 10. What is question 10? So question 10 is just conservation of momentum and conservation of energy. So for problem 10, you have 2 balls. Physics. Problem 10. So you have 2 balls connected by a spring. There's a string here. So there's energy compressed there's energy stored in the spring. And they're both moving with velocity v0, v0. So the kinetic energy of the leading ball, kinetic energy 2, this is 1 and 2, is 1/2 mv0 squared. After the string is cut, so 1 is moving with velocity v1 and v2 is moving with velocity v2, and of course the kinetic energy of the second ball is 1/2 mv2 squared, and it's increased by 21%. So v2 is 1.1 v0. And because they have the same mass, you can work out that v1 is 0.9 v0 because of conservation of momentum. So you can see that now if they were initially, and you can work out the energy in the stored in the spring. So energy stored in the spring is 1 point is the kinetic energy 2 dash plus kinetic energy 1 dash minus twice the kinetic energy 2, like minus the initial kinetic energy. That's the energy stored in the spring, and you will see. And if they're stationary, you will see a different change in kinetic energy, which is quite fascinating. All right. Anything else? Does that make sense, Alexander? Or you've solved it and you just found it annoying? Oh yeah, translation of momentum. So that gives you the velocities of the ball. All right, what about maths? How difficult did you find the maths assignment, the maths 07? This is a question for everyone. A lot easier. All right, good. Easy. Easier than the last one. Okay. What was the last one? Last one was series. Oh, of course. So what happened with series? Series was one of the last assignments, so it's probably one of the hardest ones. The rest are going to be a bit easier. So easier than the last one. Okay. Right. Good. So easier. Okay. All right. Thank you. Thank you for coming. When would we expect the marks back from the last assignment? It depends on your tutor. So we expect them to do it in 1 week. But if you haven't, maybe email your tutor and copy us in the but they should be doing it within like 10 days after you've submitted. So if this does not happen, please let us know. We'll see what we can do. All right. See you all. Thank you.